It's not working. Okay, can you hear me? So let me start this talk by thanking the organizers for the great opportunity to be here today. It's a great place, it's a great conference full of fantastic people, so thank you very much. It's a great honor for me to be here. So, the title of my talk is Quantum Spine Dynamics, Coherences, and Entanglement in Trap Ions Array. So I want to start by, this is a work that has been done in very close collaboration with the knee spinning trap group. So I want to start by thanking my collaborators. In particular, let me start acknowledging the work in John Bollinger's group and his great group of postdocs, and in particular, Justin Bonnet, who did most of the measurements that I'm going to talk about today. And I also want to thank my theory team. In particular, I want to highlight the work by Michael Wall, Martin Gassner, Agar Gavan-Zafani, and Michael Foss-Fife, who is now in ARL. All right, so my talk is in non-equilibrium quantum matter, and I think we all are aware that non-equilibrium quantum systems that are strongly interacting are not only ubiquitous in matter, but also are very important for advancing quantum technologies and are at the heart of understanding modern quantum science. So these systems are really, really interesting and important for us, but when we try to understand them, we always face the fact that they tend to be very complex because they are most of the time strongly correlated and entangled. And that, because of this, the standard tools that people have developed, we have developed for a very long time trying to understand equilibrium systems, they do not apply for these far-from equilibrium systems, and therefore we are in urgent need to develop new methodologies. However, there is a great developments in the last couple of years on the experimental side, and this is very stimulating because it's allowing us to try to understand these far-from equilibrium systems. And in particular, I'm highlighting here the work on atomic systems and atomic and molecular systems. So now we have heard beautiful talks this meeting on well-standard systems that interact with contact interactions, and we will hear more about those later. But, and we have also heard great progress in more complicated systems that interact not only with contact interactions, but with long-range interactions. And for example, we have this beautiful talk by Tillman that Rydberg atoms. We are also here about polar molecules, magnetic atoms, and also trap ions. So one of the questions that these long-range interacting systems open up and we are interested to addressing is how fast entanglement and correlations propagate in those systems compared with what happens with short-range interacting systems. So I like this type of question because it's important for trying to set up the speed limits in when we can create quantum state transfer and thermalizations that recently are a very important questions that have been asked by the community. And we are always want to know the complexity that we face when we are trying to simulate the quantum dynamics of these systems using a classical computer. That is what we have so far. And well, because we want to make connections with experiment, a very important question that we face is how we are going to characterize and measurement the development of multi-particle entanglement in experiments with the fact that most of the times we have to deal with decoherence. So how we tackle the interplay between entanglements and decoherence. So my talk today is try to answer those questions in the context of trap ions. So I'm going to talk about crystals, not of droplets like Tillman talked today, but actually crystals of ions. And it's a little bit different setup that we heard on Monday because we are not talking about linear traps, linear arrays, but actually we are talking about 2D arrays. And they are really macroscopic. I mean, we are talking about between 20 and 300 ions. And you see these very nice pictures that were taken in John Bollinger experiment that shows crystals ranging from 25 to 125 for ions. So the idea is that we are trapping these ions in a penning trap. And this consists of a set of electrodes, stacked electrodes, cylindrical electrodes, that creates a very tight axial confinement. So this creates the 1D, the plane that forms the crystal, and this is stabilized them. So this forms a self-assembled lattice that is half of a form of a triangular lattice to minimize column repulsion. So the axial, the radial confinement is done by the Lorentz force that experiences a particle, a charged particle, that is rotating in the presence of a strong magnetic field along this z direction that is induced by a superconducting magnet. So this creates a strong field along the z direction, and this creates the trapping that we want. So now that we have these trapped ions, what we want to do is to encode that spin degree of freedom in them. And for that, we use a hyperfine energy levels. So we use the two lowest hyperfine levels as our to encode that spin 1/2. In the presence of this large magnetic field, actually they ended up separated by the order of 100 gigahertz. And we can do single qubit control of these spin states with a microwave. So the fidelity that we reach with those gates can be larger than 99% fidelity. All right, so this is how to encode for one qubit, but we want to make the qubits interact between the cells. And this is done in a very similar way that we heard on Monday, but it's slightly different. So we use a star shifts of Raman beams. So what we want to do is to illuminate the sample with two Raman beams that are, have a different frequency, mu. This is the bit node between the two beams. And we want to set this mu to talk with the phonons, the transverse phonons of the crystal. Then these phonons are the ones that are going to induce spin-spin interactions between the ions. So that's what we are going to do. So let me tell you a little bit more about the interplay between the phonons and the spins. So when we impose this force, so we impose a spin-dependent force, so atoms in a spin up feel an opposite force that the atoms in a spin down. So we can, in the Lamb-Dickey regime, actually the Hamiltonian that is created has this form, where we see here z is the distance, the actual distance, and mu is the bit node. And we can expand this z term in terms of this normal mode of the crystal, the transmitter mode. And in order to visualize these modes, there is this very simple movie where you can see that they are just classical drumhead modes, and we are going to talk to them. So these are, so depending on how we set this mu, we can talk to one mode or to all of them, and this is going to allow us to control the spin-spin interactions. So you can see this Hamiltonian has a phonon term and a spin term, but actually is quite simple, and this allows us to actually write an exact propagator that when we write the Magnus expansion, we can exactly cut it to second order. So this is the exact propagator that has two contributions. One contribution comes from the spin-phonon coupling, and actually, in this, for the present purposes, we don't like that because it introduces entanglement between the spin and the phonons, and this indirectly causes decoherence. What we like instead is this term, the spin-spin interactions, but we can make them dominant by having a large detuning, and in this case, this is the most relevant contribution. So let me tell you a little bit more about this spin-spin interaction. That is what we want to use. All right, so the spin-spin Hamiltonian is actually an Ising Hamiltonian with coupling constants J and J that we can control by controlling depending on the eigenmodes and the detuning of the Raman fields. So something that I'm going to use later is that you see that it scales inversely proportional to mu minus omega, so it's inversely proportional to the detuning. But so what happens is that we can make excite by choosing the detuning different type of modes. So if we are very close to the center of mass mode, what happens is that all the ions are we are only talking to the center of mass, and all the ions are moving together back and forth collectively, and because of that, the interactions are all to all. So all of ions are talking equally to each other, and this is one of the regimes that we can operate. But there is another regime where we are very far detuned, and we are very far detuned, we almost are talking equally to all the modes, and this type of detuning creates kind of power law interactions with a power that decays kind of 1 over r to the cube. So most like 1 over like type of dipole-dipole interactions. So this is experimental data that have measured this decay. For this talk in particular, I will be mostly interested in this all-to-all range when we have collective interactions. So one comment here is that you might be thinking that, well, how we are going to decouple to the phonons if we are not very far detuned. The reason is that at least when we talk to a single mode, we can choose specific times at which the phonons and the spins are decoupled. So these measurements, all the measurements that I'm going to present are done at these decoupling points. All right, so how we are going to characterize, benchmark the spin model? Well, in fact, the technique that we are going to use is type of Ramsey spectroscopy. This technique at GILA, for example, we have used it before to characterize dipole-dipole interactions, the molecules, try to measure spin interactions between the strontium atoms. So in this case, we are going to apply it for the ions. And the technique is straightforward. So we start with all the spins pointing down by the optical pumping. Then we apply a microwave pulse that rotates the spins. And then they are going to precess in the presence of this interaction Hamiltonian, the spin-spin Hamiltonian. They are going to accumulate a phase. And we want to read this phase by applying a later readout pulse that converts phase in populations. So we also are going to apply a pi pulse at the middle, an echo pulse, just to suppress any type of undesirable slow decoherence processes. So this is one way to look at this. The other is just look at a quench. When we have a large magnetic field that set the spins pointing along x, then we quench it and look at the dynamics. All right. So what are the goals that I want to have? Today, I'm going to try to verify that they actually have the spin model that we are thinking they have, that phonons are really, in fact, not important, that we are going to want to aim for creating strong correlations and hopefully go to the regime that is intractable to theory and we can create and do a quantum simulation. All right. So if you want to understand and analyze the simplest way to experiment, one of the first techniques that you try to do is a mean field approach. And in the mean field approach, what happens is that you think that the interactions can be thought as the rest of the ions generate an effective magnetic field for example, for the ion J, the other ions generates an effective magnetic field B that depends on the magnetization of the others that is set by theta, the area of the first Rabi pulse. So how much I tilt the spins by my first pulse. So this means that the full dynamics is just a precession. And well, this is actually valid for short times. And prior experiments have been able to measure this precession that agrees very well with mean field. This is for different tipping angles. And actually, that was used before in 2012, actually to determine the coupling constants and actually check that the power law dependence that we are expecting. So, well, this is quite nice on one hand, but on the other hand, it's not the full story. And you can see that it's not the full story because if you set this theta equal to pi half, then you say, well, the B field is 0, there is no dynamics, and we know that this is not the case. So we need to go to beyond mean fields, and this is the trade-off defects that we want to probe in the experiment. So actually, for this collective case, when all the ions are talking to each other, we know that they generate this well-known one-axis twisting Hamiltonian. We heard also very nice talks about that Hamiltonian yesterday, and we will hear perhaps more. But one of the intriguing points is that even this simple Hamiltonian can generate massive entanglement, well, a lot of entanglement and correlations. And you can see the entanglement that is generated by just looking at the depolarization, Sx. When imagine that you start pointing, all the atoms are starting pointing along the x direction. That is the case that there is no mean field dynamics. But when you do the full solution, you can see that Sx collapses and revives. And the collapse, you can understand as the fact that correlation between spin I that I'm measuring, this is a single particle observable, it entangles with the rest or correlates with the rest, and when we trace off the rest, then it creates some defacing. So that's a way to understand this decay, but because it's a coherent problem, as coherent systems, and then it has to revive at some point. But in the middle, you can see this cat state forming, all atoms pointing along x, or atoms pointing at minus x, a superposition of them. And well, this happens at significantly longer times. We will try to see that in the experiment, as I will show later. But here at short times, we still generate a strong entanglement, and it can be seen in the form of species squeezing. And the way that I see spin squeezing is the fact that because of this Hamiltonian, you see that components pointing close, farther from the equator have a larger rotation and in opposite direction. So this distorts the initial shape of a coherent spin state. This is the noise of a coherent state that is symmetric, but gets distorted, and some places the noise is reduced at the cost of expanding and in other directions, and this reduction of the noise can be think of as a spin squeezing. There is a way to measure that in terms of the variance divided by the length of the Bloch vector. This is the spin squeezing parameter that we will try to measure, and actually this is parameter when it's smaller than 1 is a signature of a squeezing, a signature or a witness of entanglement. All right, so this is nice. This is the case of the coherence system, but this is not the full story. So actually it happened that before, the experiments were only able to see mean field corrections. They can only go to very short times because in ion traps, at least in the penning trap, we have strong light scattering processes that decohere the sample. And before, they used to be significant, comparable even with the spin-speak interactions. So it was 2 years ago that they started to change the beam configuration, and they were able to increase the couplings by a factor of 50. And now we can see more dynamics, coherent dynamics compared to decoherence. But anyway, decoherence cannot be ignored. So decoherence makes the problem much more complicated, because if something was initially in a decay manifold, that is very simple to model. When you have decoherence, it shrinks and you have a full Hilbert space to deal with. So there are 3 types of terms. There are Rayleigh terms that just cause defacing, and spontaneous emission and absorption that they can cause incoherent flip-flops. While this commute with the Hamiltonians and is very easy to deal with, like at the mean field level is exact, these do not commute with the Hamiltonian. And fortunately, we have Michael Phosphide, and he came up with an exact solution. I have not seen before exact solutions on open problems, but he derived an exact solution for an icing model with all this type of process present. And we have used these exact solutions to actually model the experiment, as I'm going to show. Okay, so let's start with experimental observations. So first, we look at the coherent spin depolarization, that is the contrast of the Ramsey fringe, or is the length of the Bloch vector. So this is the length as a function of time. It was done for 3 different types of systems that have different number of ions, 144, 58, and 21. And what we see, well, first, notice that there is decoherence. As you can see, when they don't have the optical dipole force, still the contrast decay. This is just because of spontaneous light scattering process. But then we see that if you start to add in the dipole force, then you see that there is depolarization that is independent, and actually the independence can be fully captured if you scale as you expect from the theory. Actually, the theory lines include the decoherence. Then we can see that we really are seeing many body effects, and therefore we are seeing beyond mean field corrections at theta equal to pi half. So that's great. So depolarization is the first signatures of beyond mean field corrections. However, this is not telling anything about entanglement. So let's try to see if we can see entanglement. So that was the next type of measurements that they were done. So in order to measure entanglement, then we need to measure the variance. So these are experimental measurements of the variance respect to the tomographic angle. So we wanted to measure the variance along at an angle perpendicular to the direction of the block vector, and we want to vary this angle. This is here. So these are for different times, short times, intermediate, long times, and you see that in fact, as you expect from this movie, there is regions of squeezing, there is small variance, there is regions for large variance. So this is the squeezing, this is the anti-squeezing. There are experimental measurements. Just to emphasize, well, this is for 86 ions, and then the lines, I just want to emphasize the importance of decoherence even in the variance too. So we see that the dashed lines are not decoherence included in the theory, and the full lines are when we include decoherence. So we are seeing signatures of squeezing. Let's try to quantify the minimum squeezing that we can get, or the minimum variance. So this is the minimum variance at this optimal angle as a function of time. And this is experimental lines. This is the theory lines. The shadow line is the fact that we have 5% uncertainty in this tomographic angle, but we see significant spin squeezing, and well, we see anti-squeezing. And just to have quantification of how much squeezing we have done, we have created, this is the squeezing parameter. This is the case when I have a time equal to 0, with everything is circular, no squeezing. But then, as I start to increase the number of ions and try to look at this minimal variance, then we can see that, well, if I don't subtract the shot noise, the photon shot noise, I can reach a squeezing of 6 dBi. If I subtract the shot noise, then this I have 6 dBi. If I don't, it's about 4 dBi, but still is a significant squeezing. Well, not as large as other systems, but it's telling us that we have building up entanglement in the system. So, but notice that the fact that we have no squeezing at longer times is not necessarily saying that we don't have entanglement. It's only telling us that the squeezing is not the proper parameter because our distribution is not longer Gaussian. Squeezing is mainly for Gaussian distributions. So the question is, we can quantify how much entanglement or correlations we have at longer times. So this is the case where the longer times where the squeezing parameter is already large, but we want to see how much non-Gaussian statistics we can have in the system. So this is the spin variance as a function of the tomographic angle, and very nicely, these are the ions, the experiment can measure the full counting statistics. So along a given direction, I can measure how many spins are pointing all down, how many spins are pointing all up, and do the histogram. So these are the histograms, experimental histograms at 5 angles. So here are the small variance angle. The red line is in the case of a time equal to 0. And then the solid lines are the theory that is agreeing with the experimental measurements. And not only for here that you have a narrow fissure, but also here when you have anti-squeezing, that you can see that there is really non-Gaussian distribution. So at this very 92%, 92 degrees, we see not only agreement with the theory showing non-Gaussian statistics, but also, well, the capability to perform this type of measurements in such a large system. We are talking about 127 ions. And just a remark, so the theory needs to compute endpoint correlations, well, even 2n sometimes correlations to actually compute this type of histograms in the presence of the coherence. So it's not an easy task. We are able to compute that using the permutation symmetry of the all-to-all coupling, but in general, if we go to a system that is not all-to-all, this type of theoretical calculations are going to be impossible. All right, so these computations of these measurements of the counting statistics allow us to even compute the Fisher information. That is another entanglement witness. We need to compute the distributions because we have an open system, and a way to characterize the Fisher information that is one entanglement witness for the case that you don't have Gaussian states is through the so-called Hellinger distance. It's just the sensitivity of your state to small rotations, and when you expand the distance of this distribution, the term that goes next to the theta square is the Fisher information. So from the histograms that I showed before, We can do theoretical calculations of the fission information. Then if we had no decoherence, we would have F divided by N of 34, meaning 34 particles entangled. But, well, we have decoherence, and it goes drop to 2.1 in the presence of decoherence with no shot noise included. When we include shot noise, we are below the region where we can use fission information as an entanglement witness. So in this case, we don't see that when we add photon shot noise. So in the last minutes that I have, let me tell you a little bit about a new strategy that we have developed trying to characterize the development of correlations and coherences in a many-body system. And for that, we try to borrow some concepts that people in NMR have developed for that. So what we are going to measure is the so-called multiple quantum coherence spectrum. That is a technique developed in NMR trying to use very simple measurements to characterize the evolution of many-body correlations. So briefly speaking, this is what they do in NMR, and the only important ingredient that you need to have is the capability to reverse your Hamiltonian. So in NMR, it's almost a finite temperature, so it's almost a unit density matrix, but you have, if you can introduce some polarization along the z direction, and what they do is that they want to evolve this density matrix with a Hamiltonian that introduces flip-flops, pair of flip-flops, and this is called the double Hamiltonian, double coherent Hamiltonian that is done using the dipole-dipole interaction with a sequence of pulses. So after they apply this sequence of spin flips, pair of spin flips, they want to see how many multi-particle coherence they have developed at this time tau. And for that, what they do is that they apply a rotation, then undo what they have done before, and then they measure SC. And these SC measurements, the Fourier transform gives information about this multiple quantum coherence. A brief explanation that I can provide for that, although it's brief, is the following. So the density matrix can be, think of blocks that have different coherences. For example, this is an example of 3 spins. I can have m equal to 3, the maximum number of flip-flops, the terms that have non-zero elements between all down and that is 3 down and 3 up. We have the terms that have the same spins and flip to 1, flip 2, so forth. And what happens is that if you do the math and you compute SC, that is the density matrix at time equal to 0, you see that after the time evolution, when you measure it, then the Fourier transform of this gives information of these multiple quantum intensities that signals multiple quantum coherences. So the requirement for that was the possibility to invert the many-body Hamiltonian and just to measure the initial state. So what I want to tell you is that we have done the experiments in the ions. So what we have done is that the capability to actually reverse the sign of the Hamiltonian by changing the detuning. So we point all the atoms along the x, we apply this Hamiltonian one-axis twisting, we apply the rotation along x, and then we change the sign, and then we measure. And what we measure is the initial state, that means measurement of a fidelity. So we measure the fidelity, do the Fourier transform, and look at the embodied coherences, and then this is very ambitious, so we also look at the magnetization, and from the magnetization you can show that you can show embodied correlations. So this is a cartoon of what we should expect to see if you had perfect no decoherence for 100 ions, the fidelity as a function of time. You see the M component, how the coherences develop. They start all 0, but at the cut state, you have M equal to N and M equal to 0 develop. This is the propagation of the multi-quantum coherences. If you look at the C, it's very nice because you look at the build-up of many-body correlations just with a single particle measurement, how they propagate as a function of time until we reach the cut state. So because I'm running out of time, let me show you briefly the results of the experiment. We did the experiment in N equal to 48 ions. They were able to measure the fidelity in that. Of course, the fidelity decays with a factor of n, so the times were reduced. But we were able to detect up to 4 coherences. These are theory lines that we need now to include even the phonons to match the experiment, but we can see the development of up to I4 coherences in the system. But we are also measuring the SZ component, and actually what we see is that develop up to M equal to 4 correlations in the system, in a system of 111 ions. So these are the experiment, these are the theory, they're the different coherent components, and just let me finalize that this multiple quantum coherent spectrum can be very powerful. So we can connect I2, for example, with measurements of concurrence. We can connect IN with the measurement of cat state fidelity. We have established that the IMs can be a lower bound of Fisher informations, and lately we can even see that maybe it's relation between entanglement entropy. So you see this is the measurement of I0. You see all these wiggles, and they fully agree with the wiggles that you find if you compute the entanglement entropy of the system. So in principle, this could be a very powerful tool for the future. And just let me conclude. I think there is a great vista ahead. You are just starting. We implemented Ising interactions all-to-all. We see cat state. We see beyond cat state Fisher information, non-Gaussian statistics. But in the future, we want to apply transverse field, add variant range interactions, decrease the coherence, and finally look at a single ion resolution and readout. And with that, thank you for your attention.
Okay, thank you very much. So I'm looking for questions. Yep, one at the front.
This is a very wonderful talk. So may I ask you, when you simulated the EC model, because the EC model we usually consider about the nearest neighboring, the interaction. But in your case, this in the ion lattice, I think this is a long-term interaction. So this is a different model. So why you can use this long-term interaction to simulate the Ising model?
Well, it's the same sigma C interactions. You know, in principle, the basis is a states pointing.
But for EC model, this is sober. So this is, we only consider about the nearest neighboring interaction, not in another far side neighboring interaction. But you, in the ion traps, I think this interaction is a whole interaction between each other.
Yes.
So
we can tune it, but in this case, what we have considered is the all-to-all case. It simplifies the calculations if you don't have the coherence, because instead of coherent, need to consider 2 to the n states. Now you only are in the decay manifold that everything is fully symmetric, because we start in a fully symmetric state, so it's n plus 1 states. So the dynamics in principle can be quite simple without the coherence.
Okay, so the second question is, when you change the parameter, so there are several fast transition diagram. So we should, in experiment, should observed. So what's the kind of fast transition diagram you observed in this experiment?
Fast transition.
Fast transition.
Phase transition.
Fast transition.
Okay,
yeah.
so far we have explored dynamics. So we are doing very rapid quenches. So we are not doing any type of phase transitions in the system. So it's just dynamics. At some point when we add the transverse field, we should be able to reproduce some of the measurements that were done in other trap ions group that you can try to go from, well, you can see the Ising transverse field phase transition. So far, it's not. So it's just pure dynamics. But okay. It opens, so that's one of the next stage that we want to explore.
Okay, thank you very much.
Okay, maybe one more question, if there is one quickly. Right at the front.
The phase transition of ion is first order transition or second order transition. You measure the fidelity in the torch, you know. There are relation between the fidelity and the quantum phase transition.
Yes, in principle, we have not measured those. So far, we are only restricted to dynamics. So this is not, there is no transfer field, anything, so no phase transition at all. So it's just the pure Ising model without the transfer field. When we add the transfer field, then we might, well, hopefully we can see some type of phase transition. And, well, in principle, we can see how much this tool could be used to. So they can measure fidelity, but let me tell you that For measuring this fidelity, it was very important. We are actually measuring the fidelity of being all dark because we can distinguish all dark from one flip. But because of photon shot noise, it's going to be very hard to distinguish one up or two down with that large control. So fidelity so far is only measurements in the all down state.
Okay, so I think with that I should close the session. So let's thank Anna Maria and all the speakers.
Okay, may I have your attention, please? I have a very important announcement for on-time departure of two kinds of afternoon tours. First, for DMZ tours, there will be